Okay, I am Pushmeet Kohli. I'm going to talk about robust artificial intelligence. I cannot actually see the the question, so after a while, I'll basically sort of check, and if there are sort of questions, I'll try to sort of reply to them. Okay, so I'm a research scientist at DeepMind, where I lead the science, robustness, and reliability teams. And I'll be talking about robust AI. So we know AI and machine learning can help solve some key impactful problems in the world today. We have seen how machine learning can be used for problems which are relevant to climate change by making more efficient use of renewable energy sources, or by reducing our power consumption in things like data centers. More recently, we have seen how machine learning can help us even make understand how biology works. Our more recent work on AlphaFold was able to do really sort of accurate in silico sort of predictions of protein structures, which are relevant for many different sort of areas, including understanding disease pathways and how different viruses or organisms interact with our bodies. But when we think about these sort of problems, how do we check that a particular problem has been solved by machine learning, or we have found a system which is actually which is working as intended? Just to give you an example, let's consider image classification. Now, a key sort of data set which spurred the more recent sort of deep learning revolution is ImageNet. And if you look at these 15 images taken from ImageNet and consider some of the state-of-the-art classifiers, you will see that these classifiers are able to accurately sort of recognize a wide variety of images and different types of species, so different object categories. So I would have trouble identifying the names of the species of different sort of birds, cats, and dogs that are being shown on this slide. Yet our latest sort of computer vision image classification systems are able to make very accurate predictions on these kinds of images. In fact, they are perfect on these kinds of images. So is image classification solved then? Well, if you take the same state-of-the-art classifier which performed really well on these images, and you run it on these two images, which to us look the same, it would label one as a school bus and the other as an ostrich. And this is a very surprising sort of result, because when we reason about intelligence, we somehow work with under the bias of human intelligence. If a human was able to recognize all these sort of species of different birds and cats and dogs, we would assume that they would, of course, say that this is the same sort of category. Yet the machine learning system is making these crazy predictions. So what's happened here? The thing that has happened is that we had some assumption in our mind, and that assumption was sort of broken. And the assumption was that a computer vision system or image classification system should be insensitive to imperceptibly small changes in the input. Right, to sort of define it formally, if you have your signal and it is bounded, and if you make a change which is an extremely small change in the input, then the classifier's prediction should be the same. So this was an assumption that we were making, and this sort of classifier, the state-of-the-art classifier, was not consistent with this particular property. So when we think about image classification, if image classification is solved, we can infer that, of course, we would have solved ImageNet or MNIST. But if ImageNet or MNIST have been solved, we can't sort of make the inference in the other direction. Like ImageNet or MNIST do not sort of, success on ImageNet or MNIST do not sort of, does not imply that the problem of image classification has been solved. And this is not true just for image classification. This is all over the place. If you now consider another problem where machine learning has made significant advances, the problem of machine translation, you look at a simple sort of a model which was state of the art a few years back, a sequence to sequence model for translating German into English. And this sort of model sort of produced a very reasonable sort of blue score. And if you give it this particular input, it correctly sort of translates it into the right sort of English translation. Now, if you had given this input to a human, the human would basically and you would expected this sort of a result. Now, if you give another input, like which does not make that much sense in this particular case, you don't expect the human to go into an infinite loop or basically to just start producing rubbish. But this is exactly what this state-of-the-art system sort of does. It performs really well on the instances it has seen in the training set. But when you just artificially create an instance, it somehow sort of goes berserk and starts producing these very crazy outputs, something that we would not sort of expect. And here, the property that this system fails to be consistent with is that the output size should be basically similar to what we are inputting, right? You don't want to give an input which is like 3 words long and produce an output which is like 3,000 words long. In some cases, that might well be required, but not in sort of in most cases. Here's another example for the problem of entailment reasoning, where you want to where the machine learning system has to make the prediction whether the sentence on the left-hand side entails the sentence on the right-hand side. And this model is a very sort of is one of the state-of-the-art models, and it is able to produce the correct entailment probability, like a high entailment probability. Now, what happens if we just try to remove some words from this from the left-hand side sentence? It seems that this model was in fact not really understood the whole idea of entailment. It just sort of was looking at certain sort of words and using them to make the prediction of entailment. For just the word boy, it gave a very high probability of the statement, a boy holds a toy, which is absolutely not sort of true. So in this particular case, the system is sort of inconsistent with input uncertainty. If there was less sort of information in your input sentence, then you shouldn't sort of be more certain about this particular sort of entailment relationship. And this is not just true for sort of sequence structure prediction models or classification models. If you now consider generative models, where here's sort of a normal sort of VAE model, and if you take this particular input, you will see a reasonable sort of reconstruction. Now, suppose we add some sort of noise to this input. What would you expect? Ideally, you would expect the same kind of image, or maybe a slightly sort of different image. And what we showed recently in an upcoming sort of ICLEAR paper, that VAEs are also very sensitive. Like even with some small amount of noise, you can completely change the signal. So you can produce completely different image, a completely different image with a completely different semantic sort of context by making these small changes to your input. So that the representation here is not robust to these some meaningless changes in the input. So here the encoder is just oversensitive to meaningless changes in the input. So what's sort of going wrong? Essentially, our whole sort of paradigm is focused on empirical risk minimization. We have our true Bayesian risk, and then we try to approximate it with the empirical risk. And there are sort of and this sort of works, but there are two issues. One is that our data is biased. There is no the IID sort of assumption that we make is not true. And the other thing is that the data is limited. We have a finite number of instances, and this is a problem in safety critical sort of applications where your loss function is not bounded between 0 and 1. Your loss function can be sort of between sort of 0 and infinity. And so like even small number of instances might not occur. Even if you sort of miss one very sort of large loss event, you are not able to sort of estimate your risk properly. So we have seen that these machine learning models can sort of fail to be consistent with a number of these seemingly sort of good performing sort of models which have quite good performance on our benchmark sets are able to perform really well on those benchmark sets, but somehow um, but somehow they sometimes fail in completely sort of unexpected ways. And this is not just the case for machine learning systems. The software industry has sort of suffered from this for a number of decades, right? Whenever there is complexity, a system sort of works, and then it can fail in some in unexpected sort of ways. So what are the lessons that the machine learning community or the AI community can sort of learn from the software industry, where again we were where sort of programs of large complexity were being developed? So the first is failures happen, right? And in order, and you sort of see the Windows blue screen of death, and that's something that has sort of now sort of reduced in frequency, but you still sort of see computer failures which can have dramatic impact. A few years back, the whole of Heathrow sort of came to a grinding halt because there was a bug in one line of code. And the programming sort of the software industry basically focused on formalizing what is correct behavior by specifying how programs are supposed to behave, at least. And these are not sort of complete specifications of the overall behavior, but like even partial sort of specifications of properties like memory safety, termination, and so on. And then this led the industry to focus on rigorous specification guided development and testing sort of methodologies. And so what I am proposing here is to sort of augment our empirical risk minimization based sort of approach, where we use the training data and apply learning to sort of extract or distill that data into distill knowledge from the information that we have. We sort of augment it with formal specifications if we have them, to make our model less biased and more accurately sort of capture its real performance. Now here, like I have to say, like sometimes people sort of think that if a data is limited, only small data sets can be limited. If you have a big data set, then you don't have this problem. Just to mention, big data does not imply good data. You might have sort of a very large data set which does not have variability, and that's not sort of a good data set. A good data set has to cover variations that are expected in the real world. So I could have sort of titled my talk, instead of towards robust artificial intelligence, towards specification consistent machine learning systems, and that's what I'm going to sort of focus on. So what do I mean by specification consistent AI? Like what types of specifications or properties I would want that we would want our machine learning or AI systems to be consistent with. So some sort of abstract high-level sort of properties that we can think of are safety, reliability, and trustworthiness. What do we mean by safety? So by safety, we mean that our systems should not violate safety constraints. They are robust in adversarial environments. By reliability, we expect our systems to generalize to real world variations and know what they don't know. They should be uncertain for they should basically they should sort of produce outputs which are uncertain if they are if they encountered sort of inputs which are out of distribution. And they should be trustworthy in the sense of they should be explainable, fair, and privacy preserving. So when we think about specification consistent AI, there are two sort of big steps that you have to think about. One is, how do you formalize these specifications, or how do you provide language in which system designers can describe the desired behavior? And the second is, how do you develop methods that can make machine learning systems compliant with the specifications that have just been formalized? So there are these two sort of key important sort of elements to how do you make specification consistent machine learning or AI systems. And I should emphasize here that when we think about in the what of what, how do we formalize these specifications, the focus is, I don't think computer scientists are in the position to specify what privacy should mean, or fairness should mean, or interpretability should be. It's a discussion that have to sort of be had with the wider society and community. But what computer scientists can work on is sort of provide a language in which these desired behaviors can be expressed and can be incorporated in with a machine learning system. So I already gave you an example of a specification, invariance to small, meaningless sort of perturbations. Just to give you a very concrete sort of example, if you have an MNIST digit 8, and you have your neural network and it's supposed to produce 8, if you make some adversarial perturbation, these minimal sort of changes, and those changes are the LP norm of those changes is bounded by some sort of quantity epsilon, then you want that the prediction, the output of the neural network or your machine learning system on this new sort of input X dash should be the same as the output of the original sort of input. And in this case, we see that in fact this is not the case. Like here, this 8 had been adversarially perturbed, and the neural network misclassified it to 3. Now, these are these examples of specifications are quite simple, and they only sort of talk about insensitivity to small, like almost imperceptible sort of changes to the input. So this is definitely like humans do not fall for this kinds of these changes. But more generally, when we think about invariance, we should think about invariance to semantic preserving transformations. So if you have digits, if we have images of digits, the predictions that we should make should be invariant to the color of the digit, the size of the digit, like any rotations or any brush trials. So any semantic preserving transformation that is applied to the particular instance. In the case of faces, it could be skin tone, skin color, hairstyle, hair color, whether somebody is wearing glasses or not, and so forth. So how do you? So there's a challenge, right? The previously defined analytical sort of specification was very easy to describe analytically, right? I just said the LP norm of the difference between the adversarially perturbed input and the original input should be bounded, right? And if it is bounded, then the prediction should be the same, right? That was the property that I wanted to sort of maintain. But how do I sort of analytically encode these semantic preserving transformations? How do I even sort of analytically describe what are appropriate sort of transformations in terms of changing the skin tone or changing the eye color or whatever? So here, one of the ideas that we have been sort of working with is to transform the images using latent interpolations, where you leverage disentangled representation like such as those produced by models like StyleGAN, and this allows you to create data with variations in latent space. So now if you have two sort of images, and one image has certain attributes in terms of its skin color or the orientation or the pose or the hair color, and some other image has some other attributes, by interpolating between in between these two sort of images in latent space, the idea is that you are trying to capture the variation that exists in terms of those attributes. Okay, so this is not a complete characterization, but it's probably better than just using those images as training data. And this allows us to sort of generate a wide variety of sort of images. So you can see, you can take images of faces from, this is from the Celeb A data set, and you can create sort of images of different sort of skin tones, makeup styles, hairstyles, and so on. So this sort of gives you a much sort of a much richer property. Now the idea would be that if any of this transformation is applied to the image, the underlying sort of attribute, like if you're doing face recognition and the identity of the face, or if you were sort of doing any other sort of classification, whether the person was smiling, whether it was gesture recognition or sort of emotion recognition, or whether somebody is sort of wearing sunglasses or not, that further sort of classification should be invariant to these changes or in these types of attributes. So I'll just stop and sort of see if people have sort of questions on the part that I just described. So I'll give you sort of a couple of minutes, and then I'll sort of I'll check again if people have questions. So please feel free to sort of add those questions, and I'll sort of reply to them, or we can go and answer them at the end. So here talking about how to formalize, or giving some examples of specifications or properties we might want to enforce on machine learning systems. Now, the other sort of big element of developing this robust machine learning systems is how do we make our systems consistent with these specs that have been defined. So if we look at what has happened in the software sort of world, there are three sort of methodologies that people have sort of taken. One is rigorous testing, like you really check your models rigorously for violations in terms of these properties. Then there is about then there is about developing robust AI in the sense of integrating these specifications during the learning process. And finally, there is verifying AI, which is how can you formally prove that a machine learning system is consistent with the specification that you set out to prove. So I'll just talk about, just give examples of some examples of work that have happened in these three areas of rigorously testing compliance of AI systems with certain properties, sort of incorporating specifications in the learning loop, and finally sort of trying to formally verify whether a specification has been satisfied by a machine learning system. So in terms of rigorous testing, like when this whole idea of adversarial examples sort of came up, most people were essentially sort of using some like trying to optimize this kind of objective. You're trying to sort of maximize the loss by sort of adding some perturbation sort of delta for the example of for the L infinity sort of perturbation example that I showed earlier, where this delta is bounded uh, by this sort of L infinity ball with the radius epsilon. And they were sort of very simple sort of techniques focused on projected gradient descent or some variants of gradient descent. So we looked at some of these methods, and there was a competition in 2017 for people to propose defenses. And there were a number of techniques that were proposed. And so we decided to evaluate whether these systems are really sort of robust. So you can categorize some of these methods under these 5 different categories, some which these kind of techniques which these models were sort of adopting. Like many models were using non-differentiability to make attack against them harder. Some were using generative modeling to make their models more robust. Then there was a technique of adversarial training, where you sort of try to find the adversarial examples and add them into your training set. And then other methods were using stochasticity and denoising as techniques. So we looked at the reported accuracy in these various papers, and then did a re-implementation, and that re-implementation yielded what is shown in the third column, this under the standardized evaluation. You can see that roughly the trends are similar. The numbers are slightly different, but the trends from our re-implementation were fine, were similar. But what happens if you slightly sort of make the optimization sort of approach for solving this optimization problem here? If you try to sort of make your adversary slightly sort of stronger than what had been used in the literature, you see that the accuracy of these systems under these adversarial perturbations drops down dramatically. In fact, for some of these techniques, the adversarial accuracy goes to almost 0. So it's important for us to recognize that we need sort of more powerful methods for rigorously sort of evaluating AI sort of systems. So now let's sort of see what we mean by developing. What is the sort of problem with developing machine learning systems which are consistent with these properties? So here's sort of a toy example of a neural network, and then it has these sort of linear convolutional layers and some nonlinear sort of ReLU layers, and finally you have a fully connected layer and some logits which are sort of making the prediction for this particular MNIST digit. Now, I will try to sort of explain what really is the problem when we try to sort of make these kind of neural networks consistent with specifications like the prediction should be invariant to small perturbations. So here in this example, you see that the original image is depicted by this dot. And this pink region, this box around that dot, are all the possible images which are at a distance of epsilon, or at a L infinity distance of epsilon or lower. So there's a whole volume of these images which are within this ball, and we want to make sure that all of them take the same label under our specification, because our specification was that if there were small changes, then the label should not change around these sort of training images. So let's see what happens when we take this image and pass it through the neural network. Now, of course, your sort of your sort of original image, when it moves through the neural network at the linear layers, nothing much happens. You get these activations. So now the dots in the second in this sort of figure represent the activation vector. And what has happened to your sort of nice L infinity box is that it has gone through a linear transformation. But when it goes through a nonlinear transformation, like say value and so on, it sort of shatters, and there are a lot of different facets to it. So it becomes a extremely non-convex sort of shape. Um, and then you look at the decision boundary, and the decision boundary basically your sort of x is your final sort of logits are on one side of the decision boundary, and that sort of allows you to make the classification. But now you see that there were some images for which were on the other side of the decision boundary, then these are essentially your adversarial examples. Because if a perturbation had been added which corresponded to sort of points on this other side of the decision boundary, then they will be given a different label. So ideally, we would not want any of these sort of points to be given this other label. They should all be in the same side of the decision boundary. So what can we do? So a very simple thing that you could do is basically do data augmentation, right? So instead of just taking that one single point, you can take a large number of, you can just add some noise, bounded magnitude noise, and then propagate it, and look at its all the activations, and look at the loss incurred by all these sort of points, and try to make sure that the decision boundary is classified. The decision boundary sort of classifies all of them to the same label. But now you still see that there is some sort of volume which is still on the other side, and if there is a adversarial example generation method which is able to find those, then your adversarial accuracy would suffer. So this is where the idea of adversarial training came up, where you systematically try to sort of find out how I could find an example which violates or which is on the other side of the decision boundary, and then you add it to your training set. And so this approach works very well, but still it's not able to cover, it's not guaranteed to cover the whole sort of space. And there are, in this particular case, you still see that there is a small sort of chunk which is still remaining. So some people sort of ask me, like, why doesn't this data augmentation strategy work? Like, you could add more inputs. And you have to sort of realize that the volume of that you are dealing with is extremely large. The possible number of images here are like is very large, even for the small MNIST images. So it's very difficult to sort of cover the whole volume by just sampling. You have to be more systematic. So one sort of issue with adversarial training is that it's computationally expensive. You have to do this this gradient, and you have to do this optimization in the inner loop of your training iterations, which is tricky. And the second sort of limitation is that even if you sort of train it with, say, 10 steps of like projected gradient descent to find the adversarial example and add it to your training set, if you now increase the strength of your attack method or of your evaluation method, your accuracy sort of decreases. So here this sort of plot shows that your nominal accuracy is 70 for this sort of robust model, and for under a 10-step projected gradient descent attack, your accuracy sort of goes down to 53%, and the attack success rate is only sort of 7.63%. But as you increase the number of steps, as you make your sort of adversarial attack more powerful, you see that the top one accuracy goes to 36.91, then 32, and then finally 29.5, right? And the attack success rate is sort of increasing, which means that the optimization was able to find a point which did not satisfy the specification. So I'll just check if people have any questions. So there don't seem to be any sort of questions. So I'll just take them at the end. So there were these two limitations. One was that adversarial training is computationally expensive, and the other is basically it's prone to stronger attacks. So even if you train it with 10 steps, like if you then evaluate it with 100 steps or 250 steps, you're not guaranteed to be sort of robust to those. Now, if you analyze the actual sort of prediction surface, this is you find that when you train with a weak adversary or with no adversarial training, or adversarial training with a small number of projected gradient descent steps, the actual classification surface, the gradients around it are are not very well behaved. And essentially what the classification sort of surface is doing is trying to get you these valleys where a small a not very powerful sort of adversary would fall into one of these sort of valleys and would not find the true sort of adversarial example. And this works both ways. If your weak adversary might not be able to find the example, so you are robust to sort of weak adversaries. But if you have a strong adversary at evaluation time, then your accuracy would be low. And when you train with a very strong adversary, then you see that actually the model is very well behaved, and there is it's very smooth, and it's very easy to find the adversarial attack. And in this adversarial image, and in which case both at training time and at test time, you are able to find it. And at training time, if you are able to find it, then you put it in. Then adversarial training becomes much more effective. Now, so this sort of motivated us to look at the actual like regularizers to reduce the actual curvature of your mapping. And so we proposed this local sort of linear regularizer, which promotes local linearity of models around the training data. And you just sort of augment your normal cross entropy loss with this particular regularizer. And what you see is that this regularizer is able to sort of produce these prediction services which have much lower curvature and are much more well behaved. And when you actually evaluate them for consistency with these kind of specs, you see that under for these different types of attacks, where adversarial where nominal with vanilla or adversarial training with just 1 or 2 PGD steps would completely fail. Even with 1 or 2 steps of projected gradient descent, you are able to produce very high adversarial accuracies or accuracies under adversarial attack. So in this particular case, your nominal accuracy is 90, and under adversarial attack it's 46, while with just adversarial training you were going from 76 to almost 0%. So this was the local linearity sort of objective that you were that we were using for to augment our cross entropy loss. And in the case of adversarial training, you are taking your cross entropy loss and adding this adversarial objective. And so this objective, like the local linearity objective, leads to much more well-behaved sort of models. And this is not just for CFAR; it's true for ImageNet as well, that you get much better results. Now, there's a problem that which I've already sort of referred to, which is that whatever sort of model you get with adversarial training, if you have a stronger adversary, then it's able to sort of find. If you have a stronger or more rigorous evaluation approach, it's able to sort of find an adversarial example. So what we would really like is an approach which can provably sort of guarantee robustness. So what we would want is somehow, like going back to the previous depiction, is basically some sort of a guarantee that our whole area here, all the logits here, are on the right side or on one side of the decision boundary. So these logits correspond to all possible perturbations, and all of them are on one side of the decision boundary. So that's what we would like to sort of guarantee. But of course, we can't do this by just sampling. because the number of images, the number of possible sort of input perturbations is infinite. Um, so what people have proposed is various forms of sort of relaxations where you try to look at this polytope of possible sort of activations and possible sort of logits in this particular case, and you try to approximate this region with a convex polytope. And if and this convex polytope has the property that it's an over approximation to your volume of sort of logits corresponding to all possible input perturbations. And if you can now prove that this whole convex polytope is on one side of the decision boundary, that it's not intersected by the decision boundary, then you're done. And there has been a lot of research in making sure that you can make this sort of convex polytope sort of tighter and retain sort of efficiency, which has been quite challenging. So what we sort of did a few years back was take away a simple idea that a sort of a simple relaxation that had been proposed earlier in the community, and then try to incorporate in the learning loop. So this is a very simple approximation to this sort of a polytope called the box polytope, which is essentially sort of just doing sort of axis aligned sort of relaxations of this. So it's a very weak relaxation. Yet what happens is, if you now put it inside the learning loop and make the relaxation as part of your learning objective, you somehow sort of see that the model itself changes, the neural network sort of the weights change such that the relaxation becomes tight. So this approach was very effective and led us to produce some of the best state-of-the-art sort of results on verified accuracy, verified adversarial accuracy for these kind of models. Now, I've spoken a lot about adversarial evaluation in the context of image classification, because that's where a lot of this literature sort of started. But this idea of checking properties or adversarially or rigorously testing is not just valid for image classification, as I had sort of shown in my motivation slides. So we have done a bunch of case studies, and I can quickly go through them in the final sort of 10 minutes I have. So one was this adversarial evaluation of encoders or generative models. So I had shown you that a small amount of noise can completely change the reconstruction generated by a VAE. So to resolve this, so what we were essentially sort of the property that we were trying to enforce is that if you make some changes to your input, and these are small, meaning changes which should not change the semantics of your your image. So if the LP norm between your original your image XA and XB is bounded by epsilon, then that should mean that the latent representation that is produced by the encoder should be bounded by some other quantity. So suppose we wanted to enforce this sort of property. So how would you go about doing it? So what we sort of did is basically augmented the normal sort of VAE objective, which is focused on, which has various terms, some focusing on data fidelity, the prior fidelity, and entropy, and change the entropy term with this entropy regularized Wasserstein sort of term, which now really sort of made sure that the latent representations corresponding to those two images, the original image and the adversarially perturbed image, those sort of latent representations are close. And then to evaluate this model, what we are going to do is we are going to take the representation that the encoder sort of learned, and then use that representation for downstream tasks, like for training different forms of classifiers, like whether in the case of these face images, whether somebody is wearing eyeglasses or whether somebody is smiling or not. So you sort of pre-train your encoder, then you take the sort of learned representation and then sort of train a number of classifiers from that representation. And then what you do is basically you try to adversarially attack the original sort of image to see whether you can change the classifications of or the labels, the predictions of these downstream classifiers. So there were a lot of different sort of classifiers. There were like 17 classifiers corresponding to like the presence of whether the person shown in the image was bald, had a mustache, had a necklace, had straight hair, wearing hat, and so on. And you can see that there are two sort of models being evaluated: the sort of normal vanilla VAE and this smooth encoder, in which we sort of made sure that the latent representations corresponding to the original image and the adversarial image were sort of similar. And so under sort of nominal accuracy for these different sort of classifiers is quite high for both these kinds of for the representations learned from the VAE and the representation learned from the smooth encoder. But when you sort of do adversarial attacks, when you sort of slightly perturb your image, then you see that the classifiers that were trained with the representations from the that were generated by the VAE, the accuracy sort of went down very quickly to zero. While even under adversarial evaluation, where you're systematically trying to find images which are close by, which are where the classifier is fooled, you see that this smooth encoder that we had learned was much more robust. So that was on sort of learning more robust represent encoders and generative models. The second case study is under text deletions. So I had sort of mentioned this in my sort of motivation slides as well. So this has been sort of this is a phenomena. This undersensitivity to text deletion is a phenomena that has been sort of known in the NLP community for a few years now, where you see that you have a premise and a hypothesis, and you sort of want to see like whether the premise entails the hypothesis. And it has been sort of observed that you can delete information from the premise and still the model, the entailment score should be sometimes increases, which should not happen, right? Because you're deleting sort of information from the premise. So so we did some analysis and we showed that, in fact, if you look at the standard benchmark that people use for doing this natural language understanding sort of for evaluating performance on this natural language understanding task, that for almost 20% of the sample, 78% of the premise words can be adversarially removed, while increasing the probability of entailment of the original prediction. So, which is saying that the model is actually not, the models which were trained were actually not reasoning about entailment at all. They were doing something completely different. So in order to sort of make these models more robust to these undersensitivity specifications, we came up with this particular specification and called it the undersensitivity specification. And then we use the same sort of ideas that I was telling you, where you try to do interval bound propagation. You look at how the activations, sort of how what are the activations and logits corresponding to sort of changes to the original input, and what is the geometry of them, and how can we make sure that all of them are behave in this particular way. So we did that same analysis and trained the whole model using interval bound propagation, and that sort of led us to sort of produce results which were much better than any other sort of method, like than standard training. Sorry. Then this thing sort of keeps on appearing by standard training, entropy regularization, data augmentation, different forms of adversarial training. So this the final sort of column on the right, this interval bound propagation training actually leads you to much better verified accuracies. So here's another case study: conformity to output size specs. This is basically whether your model terminates or not, or is the expected, does it produce the expected number of outputs. So we looked at two types of problems: machine translation and multi-MNIST. And in machine translation, you wanted to make sure that your model sort of produces outputs of a particular length. And in multi-MNIST, you are given an image which is a composition of different MNIST images, and you want to make sure that the model is producing it's like a image captioning, a toy image captioning sort of problem, where you look at the image and you sort of try to, and you have to sort of like output what are the digits in that particular image, and you want to make sure that the right number of digits are emitted, not a large number. And so the challenge here is from the perspective of adversarial training and verification is, how do you deal with the fact that this is a discrete model and you can't just do sort of gradient propagation like we were able to do for our neural networks. Yet we were able to sort of produce some very interesting results and came up with some interesting techniques to deal with this to conformity to output size specs. And our sort of methods were much more robust than the previous the original sort of models. So I have, like, we have some verification results as well. I have another case study, but for lack of time, I would just move to the final sort of concluding remarks. I think, like, yes, machine learning and AI, like, it's already having a huge impact in a number of different areas. But to really start deploying machine learning systems in the real world, we have to sort of go beyond benchmark-based evaluation and really think about how do we really capture the essence of the problem. And that sort of like, either we have to sort of make data sets which are of course we have to make data sets much more richer and have much more coverage. But of course, it would also be good to sort of augment our evaluation methodology with these certain properties or specifications, which sometimes can be analytically sort of described. The key sort of social challenge is to take evaluation beyond static benchmarks and to go towards what the software industry has sort of gone towards, is not just unit testing, but also static analysis with different types of properties. And then there are, of course, technical challenges in terms of how do you formalize these specifications and how do you scale verification and these techniques to larger, more complex models. And the concluding question, like, I will leave with this concluding question: in like 10 years time, in 2030, like, how would AI system designers and users specify a correct or expected behavior? Would we still be using training data sets, or we like communicate ourselves using language, which is an informal specification of behavior? Would we be using more richer sort of notions of conveying behavior? And then how would we evaluate and debug our agents and models? So with that, I'll conclude and see if there are sort of questions. Okay, so there is the first question is, in case study 1, why do we want to bound the difference between the latent representation instead of difference between the final output images? So that's a good question. We can do both. Like, these are two different forms of specifications. We could say that in certain cases, so the main motivation was that you would use the latent representation for downstream tasks. So if you're using the latent representation for downstream tasks, you want that meaningless changes to the input should not change the representation, right? So if something has not semantically changed the meaning of the image, then the latent representation should not change. So, which is why it made sense to capture that particular sort of specification. But you're right. I mean, for other sort of applications, for mostly sort of for generating the right kind of output, we might want to make sure that the difference between the final and the final output images should be small. Yeah, so that's a valid sort of point. Okay, the next question is, can you please give an example for specification-driven testing, let's say for object detection in the wild? So there is, so for instance, like if you have a self-driving car and you want your self-driving car to sort of make sure that it is detecting the lane boundaries correctly. Now you would want your car to detect lane boundaries regardless of the condition, whether it's sort of snowing, whether it's raining, whether like it's like the sun is on the horizon, whether the sun is overhead, whether you are in one type of sort of road or the other kind of road. So like the point is, how do you formalize sort of that variation, and then how do you sort of then evaluate consistency with that specification? What kind of data sets do you think we need for next stages, challenges that you sort of describe? So I think ImageNet was a great effort, in the sense that it really showed that the data sets that the computer vision community were relying in the early 2000s were lacking in a very significant way, and what can be achieved if you have more data. But if you look even at sort of ImageNet, it does not really capture sort of a lot of variability in terms of. So it depends on what is the task at hand, right? So I think what we will increasingly see is that so there will be sort of specifications which are task specific, and there are specifications which are task agnostic. So the specifications that I was mentioning, this idea of L infinity sort of noise, where you say that if you are trying to mimic the human, what a human sort of labeler would sort of predict, then any imperceptible change should not sort of lead to sort of changes in the prediction, right? So that's an example of a specification. But if you are thinking about and then there are sort of task-specific specifications. For example, the example that I was giving in the context of self-driving cars, you want to make sure that your data set has coverage. And the data set should not just have instances of images, but can also have analytical transformations defined over them, saying that I have this image, and I have this analytically sort of defined set of transformations, and any transformation applied to this image also should produce the same label. Okay, the question was beyond the classical traditional ones that we have. So of course, I gave some examples of the sequence-to-sequence, of machine translation, of entailment, but consider any sort of task that we would use a machine learning system for. And you can then sort of see that in many of these sort of tasks, of course, one way to define behavior is the input-output mapping, and in the input-output examples. But for a majority of these tasks, there is some other way in which you can give some information to the system about the intended mapping, the intended sort of input-output mapping. So I don't know if I have answered that particular question well, but you should send me an email for clarifications. Okay, so there are no more sort of questions. So I guess thanks all for listening, and I hope this went well. Okay,
take care. Thank you so much.
Bye-bye. Thanks, Sanjeev.